The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, Cam from Odell here. Just wanted to start by apologizing. We were supposed to do these webinars at 3 o'clock. This one was sent out at 2. I just want to thank you for coming. We have Lee from PennBarry. We're going to get going anyways. We have Lee Sexton from PennBarry. He's a regional sales manager. He's been working in the HVAC industry for just under 10 years now. Just a few housekeeping things before we get started. If you have any questions, you can ask them over on the right-hand side. There's a questions tab. Normally we get to the questions at the end. However, if they're contextually relevant, I'll cut in and we'll let Lee know, and he'll try and answer them to the best of his abilities. And then if you would like to download a copy of the webinar, you can find that under handouts. And if you have a very pertinent question and you'd like to get it answered right away, there's also an option to raise your hand. So without further ado, we're going to get going here. Go ahead, Lee.
Thanks, Cam. I appreciate the introduction. As he said, my name is Lee Sexton. I've been with PennBarry a couple years as a regional sales manager, was with another manufacturer prior to that. And today we're going to be talking about fans and two subjects there, the first being selecting the right fan and the second being system effect. Hopefully they are valuable presentations and we can have a nice conversation as we go through here. So if there are any questions, please let Cam know. I don't mind being interrupted, and hopefully it's a conversation that's helpful for everyone. Without further ado, selecting the right fan. Sorry, I just have to click on the screen correctly. All right, so when we talk about selecting the right fan, no matter who the manufacturer is, they're going to have 30, 40, 50 different models. And then there's sizes, and there's so many options, right? It can be overwhelming if you're not a fan person, if your job isn't to know exactly what the best one is for any given application. So what kind of criteria do we use when we're saying which is the right fan? The first one is going to be the performance, and by that I mean the flow and the pressure, whether you call it CFM or liters per second, and pressure, inches water column, pascals, whichever. If the fan that we select doesn't do the right performance, it's worthless to you. The second most important criteria, I believe, is where are you going to install this fan? Because there are a lot of different mounting configurations, and that's pretty important. The third, and one might even argue this is the most important thing, or should be the most important, is efficiency. Moving down from there, sound. Nobody cares about sound until it's in their building and this piece of equipment is right next to them and disturbing them, but it is something to be cognizant of. And then finally, special use and others. So there are applications where only one type of equipment may do, or you may need special listings, things like that. So when we talk about performance of the fans, there's a lot of different styles, but we can group them into certain types. And if we think about the highest pressure, lowest flow, we're talking about radial bladed fans. And really these look like a paddle wheel. So they spin fast, they're really loud and noisy. Generally speaking, they're inefficient, but they can move air at significant pressure. They're getting near the point of being a pump. Now, why would we use one? In a commercial space, you almost never do. They're really for industrial applications, creating negative pressure environments, moving things with air, things of that nature. If we keep moving further this way, you'll notice that each type of fan has a relationship between pressure and flow. And moving downward, we can see that these are our centrifugal fans, backward curved, backward inclined, and airfoil. They're all going to have a little bit different characteristics, but suffice to say that they are the next best at generating pressure for a given flow. Sorry about that. Forward curved wheels, great option if you're using them for noise characteristics, but they're much less capable of generating pressure than a radial bladed fan or a backward inclined or airfoil fan. Just the nature of it. We often see these in residential HVAC systems. So you're going to see them in bathroom fans. You're going to see them in the fan that's in your home furnace. You're going to see them in the fan that's, you know, powering the HVAC system in your car. Great for small applications. They even get used sometimes in air handling units, but you can run out of pressure quite quickly. So that's where we might start looking at like a backward inclined or near foil wheel. And then on the other side of that, you have axial fans. So whether it's going to be a propeller fan, which is just a fan on a panel without a housing, or it's going to be a tube axial or vane axial fan where we now put that into a housing and it's able to generate some more static pressure and also be ducted. Those would be the next level up. And bridging the gap is mixed flow fans. Mixed flow fans have been around for 20, 30 years and popular, but they're becoming more and more popular as they're a nice sweet spot between the characteristics of a centrifugal and an axial fan, and they have really nice sound characteristics. So that's where we see a lot of the inline ducted market moving toward. So then going into installation locations, you know, are you going to put this fan inside? Are you going to put it outside? Is it going to be on a roof, on a curb? Is it going to be inside of an air handler? These are all things we have to think about. But, you know, whereas one's going to use this mounted on a roof curb, they're never going to consider a propeller fan for that same type of application. And if it's got to be ducted in inlet and outlet, well, now you're really into either a tubular fan or a housed centrifugal fan. These guys are kind of an outlier, fan arrays. So pretty much exclusively used inside of air handlers. But they have a nice sweet spot in that you can design a system that has redundancy and a lot of ability to modulate performance based on load, because instead of having one fan, you have 2 or 4 or 8. So moving forward, you know, what's the next thing I'm thinking about? Efficiency. In a perfect world, this would probably be the #1 thing that we consider when we're selecting equipment. But the reality is that the contractor is usually more concerned with first cost of equipment than the building owner might like him to be. You know, the building owner could look at this and say, hey, for a given performance, I'm seeing one that's almost twice as efficient, or at least 15% more efficient. We'll talk about that later, but the implications are pretty big when we start looking at the cost of running that over a piece of equipment's lifetime. So when we say efficiency, what are we really talking about? We're talking about static efficiency. In general, efficiency has 3 ways that we can measure it. Total efficiency, and that is the sum of static efficiency and getting the other one, I apologize. But what we're doing is we're removing the velocity component. In an industrial application, one might be concerned about the velocity exiting the fan or entering the fan, because you may be trying to move something with that air or accomplish work. In a commercial sense, as long as the air moves through the system, we're fine. We don't get any extra benefit from the velocity component. So we're going to use static efficiency as our metric. And again, just a couple different types of fans. I picked an arbitrary point that's fairly common in the commercial world, 2000 CFM at 1 inch. And I tried to keep the size of the wheels in these fans similar, because when we compare models in efficiency, it loses relevance if we start changing the sizes dramatically. A larger fan will almost always be more efficient than a smaller fan, so long as it is capable of providing providing the amount of pressure that's being requested. So not surprisingly here, propeller fan with no housing, no ductwork, nothing on it, just moving air in a free space is going to be the least efficient option of moving air. Radial bladed is going to be the next least efficient. At this particular performance point, a mixed flow is the next in line, and then a backward inclined centrifugal and an airfoil. Generally speaking, airfoil fans are more efficient than backward inclined. So it's going to cover probably 80–90% of applications. However, a backward inclined fan is capable of generating more pressure than an airfoil fan is when needed. In the same way that it's difficult to compare efficiency directly between models and sizes and everything, sound is also difficult, but we can make some general statements about it. One of the first things that's worth pointing out is that the faster you run a given fan, the louder it's going to be. There's no way around that. It doesn't. What the pressure is and what the flow is really are quite negligible. It all comes down to fan speed. Knowing that, we know that for a given flow, the fan speed is going to be higher on a radial bladed fan, and just the characteristics of the housing, the way it's built, the interface between the wheel and the funnel and the outlet. Radial bladed fans are extremely loud. It's not unusual to see these in the 120, 130 decibel range for industrial applications. That would be wildly unacceptable in a commercial environment. No one could have that in an occupied space and say that that's going to be okay. Vane axial fans, again, quite loud. They have traditionally been used to move large amounts of air in occupied buildings. Think about a high-rise tower downtown. You know, there's going to be some kind of corridor where they're moving large amounts of air, and vane axial fans for a long time were the preferred way to do that. But they're loud, so that meant that you needed to have attenuating equipment. You needed to have silencers, and you needed to have long runs of ductwork or insulated ductwork so that that wasn't bothersome to someone who might be physically near that equipment. Because of that characteristic, mixed flow fans, which are significantly quieter, have become more popular in those installations. Backward inclined, backward curved airfoil wheels, they're all going to be louder than a mixed flow fan, but significantly quieter than a vane axial fan. And again, forward curved fans here, the most desirable sound characteristics, not only in terms of amplitude of sound, but also the spectrum. They fall on the A-weighted scale very nicely. It's the sound that we are used to when we hear a fan. It's not high-pitched, it's not droning, it's just kind of a smooth sound that we find, you know, acceptable. So special applications, you know, this can be anything from I need to use this in a commercial kitchen to stairway pressurization for UL smoke and heat exhaust. It could be a laboratory. It could be some kind of spark resistant application, be it commercial or industrial. It could be an air handler. Any of these pieces of equipment, I should say any of these characteristics can potentially be applied to a type of fan, but generally speaking, there's going to be one or two models that fall into that. So if we're talking about UL kitchen exhaust, those are primarily roof-mounted upblast fans. Mushroom fans, spun aluminum fans, PRVs, those are all terms that we use for that piece of equipment. You can also get them sometimes as inline fans, as a mixed flow fan. You can get one with that type of rating. You can get a utility set with that type of rating, but the majority of the market is going to go towards that mushroom fan. UL smoke and heat fans, again, you know, we can do the same types of things as we can with the UL 762 fans. However, generally speaking, those are going to be inline tube axial or vane axial fans. And in the same way that the general air movement specification has gone from vane axial to mixed flow, that's happening with smoke exhaust fans as well. Something to keep in mind with both of these types of applications, both of these types of applications being kitchen exhaust and heat exhaust, is that you have some higher temperatures that you're dealing with, 300, 400, 500 degrees pretty regularly. And as such, the type of material that a unit is made out of is going to become important. If you have a fan that's made entirely out of aluminum, it's going to be a really poor choice for a smoke and heat exhaust fan. So we are kind of driving into a situation where if you need this, you're constraining the type of product you can have into housed fans that are made of steel. Less specific in terms of materials and things like that, but maybe more specific in terms of form factor is going to be in air handlers or OEM equipment. That's usually driven by a very specific space constraint that equipment needs to be in. One of the reasons those stack fans that we talked about, the fan arrays as I called them earlier, were developed were to retrofit into air handlers inside of large old buildings. So imagine that you have an air handler on the 50th story of a high-rise building. There isn't a freight elevator big enough to get, a 10-foot tall fan in there. But I can take a whole bunch of little 3-foot cubes. And that's really how that unit came to be. And as we see more and more people applying it, we're seeing new ways to control it, new ways to provide redundancy and efficiency gains as a result of having flexibility in number of fans and the speed at which they can be run using VFDs. Last thing is going to be spark resistant construction. We break that into 3 categories: AMCA, A, B, and C, with AMCA A being the most stringent, and that's effectively everything in the airstream is non-ferrous, non-sparking, and you can run just about anything through there. That's where you're going to see applications with known combustible material, be it gaseous or dust. AMCA B is going to say that I need to have a non-ferrous wheel, almost always aluminum, along with some rub plates. AMCA C is really just, it's a normal fan, but I put some aluminum or some brass around high contact probability areas. And one of the last things I would get to is, what are your geographical considerations? I'm going to guess that most of you live in or near Toronto, given that Odell is hosting this. But if you lived in Miami, Florida, you would probably be intimately familiar with Miami-Dade registration. So really the desire here was, how do we make sure that equipment people are putting on roofs is going to both stay put and function following a catastrophic storm event? So it's kind of a fun one to talk about because some of the things that they do for testing are out there. They dump extreme amounts of water on it. The one that I found really entertaining is they shoot a 4-foot long 2x4 at your equipment. It's something like 45 miles per hour. And after all these tests, you have to be able to wire this up and see it run. It doesn't really have a metric as far as how long it has to run. It just has to start, it has to run. Similarly, if you were in California or maybe Oregon here in the States, you would be familiar with OSHPD. And that was a classification that came out of the California Department of Health. Really started as a means to say, hey, following a earthquake, we want to make sure that both our hospitals and police stations have equipment that works. It has become universally accepted as the standard for seismic activity ratings. So it's a very expensive, it's a very involved process. To boil it down, effectively you have to build your equipment, put it onto a shake table, shake it, and then demonstrate that it runs. Again, no real quantitative answer on how long does it run, how well does it run. It just needs to start and run. So that's how I think of selecting the right fan. And I understand I'm not going into numbers here. That's sort of intentional. This is an iterative process, and it's something that a person learns over time. But as you start to develop a knowledge of one or two of the products, you can reference them and say, I've used this in the past, and look at something like the graphic where we have all of the different lines laid upon each other and say, what would be a good solution to something where I need a little more flow or a little more pressure? So hopefully that guides people along. Cam, are there any questions at this point regarding that material before we move into the system effect section?
Yeah, I'm glad you asked. There was a question. Where does the 6356 come from in the static efficiency calculation?
Great question. That's a constant. I have been taught how that constant is derived, but I don't remember, to tell you the truth.
Okay, thanks.
Yep. Anything else?
That's all we have so far.
All right, wonderful. So this system effect one, this is a little bit denser information, but it's something that affects us all. And hopefully by talking about it today, we can avoid it as much as is possible. You know, in a perfect world, there is no such thing as system effect, but we all know that when it gets down to it, nothing gets built exactly the way it's been drawn, and there's substitutions, and sometimes the plumber comes in before the HVAC guy, and all those other kinds of things, right? So here's what we're going to do. We're going to define system effect. What is it? You know, how is it in the lab versus the field? Go through some fan curves, some causes. Then we're going to look at inlet and outlet conditions that cause this and ways to mitigate it. And then finally, we will look at a numerical example as well as some pictures taken from the field that show problematic installations. So first, to define it, system effect, it's important to remember that system effect is not just more static pressure. System effect is measured as increased static pressure because we have to put some kind of measure to it, but really what it is the result of the fan having uneven loading on the blades due to inlet or outlet conditions. It's an inefficient duct system that leads to poor performance. So when we put information in a catalog or in a program or advertise it, we are talking about ideal conditions. Fans that have been hooked up with, you know, perfectly straight duct and that have these really nice inlet flow conditions, and we have this giant room we can put this equipment in. That's not reality, right? You know, there's going to be bends, there's going to be space constraints, so all those things, you know, we're going to change that. But at least starting from a baseline, we can compare one manufacturer against another and say that we're all making claims based on a same set of information, the same set of guidelines, so that engineers and customers can look at them and compare them. So first we're going to talk about system curves. So if we look at a fan curve and a system curve, this system curve first is just going to say, how much airflow do I have and what is the resistance? And this is an exponential growth. As the airflow goes up, the system pressure is going to go up as the square. So if I design something here, I assume that, you know, 100% of my airflow, 100% of my static pressure. And remember, these are estimations that are being made by people as they lay this out. I'm assuming that if I want less air and move down here, I can continue to follow this line. And if I'm moving left or right of it, it really means that either I have done a poor job of estimating the system or the system has changed. It's no longer defined by the characteristics that I put forth. So here we still have our system, our original design point, and we have the fan curve. So for a given speed, a fan is going to produce a given amount of flow as a function of the pressure against which it has to work. It is easy to understand that as the pressure diminishes, we have more flow. As the pressure increases, we have less flow. Depending on the type of fan, that curve is going to change. It may have a hump, it may have a bump, it may have 2 or 3. But generally speaking, this is indicative of a centrifugal fan or a mixed flow fan, and to a point, a vane axial fan. So let's define some different things here. And I'm going to bring up all these tabs for now. So if I start and I say I want to design a system that has 1,000 CFM at a half-inch pressure, maybe I should back up and say I have a system that's been designed and I need 1,000 CFM. I've determined that's going to lead to a half-inch of static pressure. Now I make my fan selection. Well, what would happen if I turned it down and said I really wanted 800 CFM? I should only be competing against 0.32 inches static pressure. But in reality, what I'm measuring in the field when I test and balance this, because I didn't get my 1,000 CFM, is that it's 800 CFM at 0.65 inches, 0.15 inches higher than I expected. And I'm not getting that same kind of flow. So what we're going to have to do is we're going to have to speed this fan up. That's what happens as we move this curve out. As we move the fan curve out, really that means we're increasing the speed of the fan. And this system curve, we had estimated it here, but hey, it actually turns out that there was more resistance in the system than we thought. So now we are moving from this original design point 1 up to 4. So now we have, to get our 1,000 CFM, we need to fight against 1.02 inches of pressure. So this is an example, it's arbitrary, but that's the kind of situation that you'll run into. So that's our system effect factor. What can cause it? A lot of things. When we get down to it, it's non-uniform loading of the fan blades. So how do we get that? Turbulence, bad inlet conditions, things like that. And on the outlet side, system effect is a poor duct design that is going to lead to that velocity that has been introduced into the airstream. Now you have high-speed air tumbling around, and you have a situation where that cannot be turned back into static pressure. Given enough ductwork in a straight, smooth line, the air will eventually regain all of its static pressure. But if we start putting bad turns and transitions in there that are less than ideal, we will diminish that and make an inefficient system that has system effect in it. I won't read all of these. Cam has provided these to people for reference, but all of these are types of situations that can lead to system effect. If I had to say which one of these is the most frequently caused problem, it'd be elbows too close to the fan inlet, without a doubt. And the next one would be poorly designed transitions, whether that's an abrupt one or it's just too much of a change too fast. So we'll look at a couple quick examples. Certain types of fans, such as radial bladed fans, are going to have an inlet like this. We just have a straight walled inlet and the wheel would be over here spinning, spinning, spinning. But they're a ducted fan, so we won't have this kind of sharp transition where we're going to have swirl, we're going to have extreme turbulence that might load and unload that fan. So in addition to system effect, you might be seeing issues like stall or surge. Easy way to change that is to put an inlet valve on it. Almost every commercial fan that you see is going to have something like this. They are not always this prominent looking, but they are almost always there. So what does non-uniform inlet flow look like? What does that mean? You know, anytime if we're looking at this and saying, hey, this is the inlet and our outlet is, effectively toward our face out of the screen on a centrifugal fan, when we have these kinds of hard corners right before a fan, imagine that the air is coming in here and it's just slamming against that wall and it's going to start curling. It's going to start coming back upon itself and it's going to create these pressure waves that go back and forth and that prevent the fan from having uniform, smooth air run through it. There's a lot of ways you can do that wrong. You can do pre-rotating swirl, you can do counter-rotating swirl. Both of them can have negative effects. And we'll talk about, what we can do to mitigate some of those. The easiest one, miter that corner and put in turning vanes. All turning vanes are pieces of metal that make that same profiled shape in a reduced pattern through that corner. And what that does is it prevents the air from swirling anymore. It still may have a little bit of turbulence, but it won't be able to move from one side of the duct all the way to the other. And in that way, they're kind of like turnstiles and gates in a train station. Everybody has to move the same way, and if one guy jumps out of line, he can't screw the whole thing up. Now, here we are looking at a situation where we have turning vanes in here, and we've done this both with what we would call pre-spin and counter-spin. Ideally, we want to avoid both of those situations when we can, but it's not always possible. So in those instances, we really do like to see the turning vanes because it stops the extreme type of loading and unloading on those wheels. Thinking a little bit more about what it happens on the outlet side, it's important to understand what the velocity profile of a fan is like. It's easy to think about it all coming out of the tube or the outlet area at exactly the same velocity because it's a fluid and it should do that, right? Well, the reality is that the way a centrifugal house is designed, all of the wheels being thrown tangentially off that wheel. And because it's doing that, it's sorry, go back a couple slides. And to start off tangentially, this is wider here, so it's producing a little bit of a low pressure area, and it's pulling that air through. And as that happens, the velocity is the highest as it leaves the top of this. And it's actually negative down here. In reality, what you will see is that manufacturers put in what we call a cutoff plate that more or less goes up to the top of the wheel to prevent this negative flow area from occurring. That being said, we still have a very uneven velocity profile, and we want to make sure that we allow this some time to fully develop into a uniform pattern. In general, what we're going to say is that we want 2.5 times the duct diameter in length. So if you have a piece of round ductwork that's 30 inches wide or 30 inches in diameter, we would like to see a 75-inch long run of that duct before it has elbows, before it has splits, anything like that. Same type of rules apply to an axial fan, but because the tip of this blade is moving faster in terms of absolute speed than the interior, this is going to create a higher velocity on the outside than it does nearest the hub. Again, that 2.5 duct diameter is about where we want to stay. And that's based on a 2,500 foot per minute velocity. If you start exceeding that, you can roughly say that for every 1,000 feet per minute that you increase it, you need to add another duct diameter. For commercial applications, we ought not be running that high of velocity because we're going to generate some pretty loud sounds. So, other types of issues that can happen on the outlet, branches. So we have this nice long run of straight duct maybe, but I put a transition right here. And all of a sudden I'm getting swirl. Or I immediately put it into a T, and as you can imagine, you have a huge amount of air just hitting a wall. So not good, things we want to avoid. Okay, so we're going to run through a problem here, or an example I should say, and talk about two solutions. One, where we have a transition, this corner to turn 90 degrees, and there is no ductwork on it. It's just a 90-degree square section that runs straight at the inlet. Or, excuse me, 90-degree round section, straight at the inlet. So, to do this, we need to have some curves. I don't have that book in front of me, but if you use like the industrial ventilation guide, there is pages upon pages of tables that have examples just like this and everything else that you can imagine that will allow you to look at a situation and try to estimate a type of loss. So if we go to this table, the pertinent one here for a right angle transition in front of a fan, and we have no ductwork on it, so we have that end value that we're going to follow down. This is the line that we're on. We're going to move, and if I were to back up a couple of steps, you would see that the velocity was something like 1,017 feet per minute. So we move up from the x-axis onto this line, and where it intersects n, we're going to move over to the left side of the y-axis and say we have between 0.18 and 0.19 inches of static pressure that we're going to add. And again, as I mentioned at the start of this, system effect is not static pressure, but because we have to work against it, we pretend that it is, and we use measurements like this to guide us in a process to overcome it. So without doing all of the math, but really what we would end up doing is we would reselect this instead of saying, hey, it's a half inch or whatever it was, I don't remember the exact number. We would now say it's 0.69 inches, and we would run that, and the fan would need to be sped up. Your sound would increase, and your brake horsepower would increase. So I want to say before it's 0.25, 0.235. So now we have gone up to 0.308. So that's it. We're still talking fractional horsepower, but it's a large increase, and it's almost a 20% increase in power consumption. And we're only talking about 0.19 inches of static pressure that changed. It doesn't seem like a lot. But when we get down to it, if we look at it, if we take that fan, we're going to run it 4,500 hours, and we have a given rate, and we're still moving the same amount of air, but we've gone from a half inch to 0.69 inches of static pressure. It's an extra $36 roughly per year to run that piece of equipment. And we're talking about fractional horsepowers. So it's not hard to imagine that this could be 10 or 15 times as large in terms of power consumption, or that you might have 20 or 30 pieces of equipment just like this. So that's reason to avoid it. You know, we don't want to be consuming power for no reason. So let's look at this example again, but we're going to say instead of putting a 90-degree piece of ductwork right on the front of that fan, I'm going to have one length of ductwork. By that I mean, if the diameter is 30 inches, I'm going to have one 30-inch long piece of ductwork, and then I'm going to have a mitered corner that has a radius over the diameter of 1 as well. So that ratio is going to be 1 to 1. What that means is that we're moving on to this R curve. Same curve that we had before, but we're going to move from N all the way over to R. So R. And if we look at this, we were at right around 1,000 before in terms of velocity. That hasn't changed. So what that means is that I don't have any system effect as a result of this type of installation. That's what we want. We want to find solutions where a small change like that can be done. Now, we all understand that the installation is going to dictate issues like that. So in the spirit of showing other people's mistakes and not mine, hopefully none of yours, I've included some pictures here that show some really poor installations, and we'll talk about why. So right here, look at this. This is a conglomeration of errors. I don't think anyone could do it in the field if they wanted to, but we have a very strong transition with no effective duct length. We have a very blocked off inlet where only maybe half the surface area is exposed to duct. And then we have an immediate 90-degree turn against the airflow. So we've got, 3 contributing factors to system effect on that one. They've done it a little bit better here. You know, they have a curve and they have this nice mitered corner. So presumably they have some straight duct down there. So that inlet condition looks pretty good, but look at this. We're taking an immediate turn. These elephant-looking fans are, you know, experiencing system effect as a result of that, where if the intended use here was really just to go up, all we needed to do was turn that fan 90 degrees and point it straight up. Problem solved. I wish I didn't see so many installations like this, but I would say this is the #1 type of poor installation I see is kitchen exhaust fans mounted on things where they don't belong. Almost always you'll see some sort of really, really terrible transition to a kitchen exhaust fan on the side of a food truck. I'm sure it's a space limitation issue, but it makes me cringe every time. I don't know what's going to happen in this fan, this one here with this Venturi here, but you can imagine that there are better ways to accomplish that that don't have reductions and then immediate expansions right in front of the fan. Who knows what's going on here, but this is a lot of interesting ductwork, and it's all hanging out right in front of an air handler intake, presumably. Here we have someone who has done something really interesting with dampers and who knows what. I'm not even quite sure what's happening in here, but we've got all sorts of crazy transitions coming into this plenum box. Another situation where maybe just moving the fan a little bit further away would give us that space to have some better corners. Having dead spots in a box like this is a horrible thing. You know, once this air starts moving downward, it's gonna come all the way down there, and it's gonna start swirling. Bad news. Look at that. That is beautiful. This could have accomplished the exact same thing, just pointing that fan straight down, ducted into the roof. So that is the culmination of it. Cam, any questions that you want to shoot over right now?
Yeah, thanks, Lee. So we do have one question, and it comes from one of our reviewers. They asked, are manufacturers' engineered tapered inlet fittings effective? I believe they're called low loss fittings.
Sure. So that isn't a technical term per se. Everybody is going to have a little bit different dimensions on their inlet and outlet conditions, but in general, yes. What you are purchasing when you purchase them from any manufacturer is you're usually purchasing a device that has been tested in conjunction with that fan. So whether it works well or it doesn't work well, the manufacturer has had the ability to test that and then document it and allow you to effectively understand what the system effect is going to be. One type of transition that's often supplied with fans is like an outlet évasé. Not particularly common on commercial fans because we're not running them at the outlet velocities where they're required. But in an industrial application, you may have an instance where you're running at the 5,000, 6,000, 7,000 feet per minute range on outlet velocity, which is very high. And if you imagine that you expand that air too quickly, you'll get cavitation, you'll get severe turbulence, and all those sorts of things. So really what we want to do, whether it's an inlet transition or an outlet transition, is that we want to try to avoid making any kind of change in the profile that's more than 7 degrees off of either side. And that just has to do with the rho value of air and its ability to change directions while staying in a semi-turbulent or a laminar flow. Hopefully that answers the question.
Thanks, Lee.
Is there any other questions that people would like to ask at this time?
That's all that's on there as of right now.
Okay. Well, I appreciate everyone taking the opportunity to watch this and allow me to talk at you. If there's any questions, please feel free to reach out to your folks at Odell, or if they can't answer it, we'll be happy to help them. And enjoy the rest of your afternoon. Hopefully it's sunny like it is here in Minnesota, and best of luck with the coming weeks.
Thanks, Lee, and thanks again, everybody, for coming to our isolation intelligence webinars. We're gonna be moving back to our 3 o'clock time slot starting on Monday. We have a special presentation done in part by myself as well as United Enertech, who we're going to talk about the recent updates to the building code and the smoke and fire dampers. And then we have one on Wednesday at 3 p.m. with Envirid. They're going to be talking about their heat load reduction technologies. So stay tuned for the emails that come out about those. And thanks again. And thanks again, Lee.
Thank you, Cameron.
Oh, one last thing, everyone. You can find the copy of the handout and the download, or the YouTube link, sorry, for the video of this webinar on our website in the coming hours. Take care.